This is section 8.2, inverse and joint variation. Yesterday we talked about direct variation. Today we're going to talk about these two new types of proportion. Our goals today: to explain inverse variation and solve problems with inverse variation, to define joint variation and solve problems with them, and finally to solve problems that combine different types. So using a relationship that we know that rate times time equals distance. Assuming the distance doesn't change, and let's think about it this way. Let's say you live a mile from school and you walk every day. If you walk faster, it'll take you less time to get there. If you walk slower, it'll take you more time. So if d is constant, the speed increases. If the speed increases, then the time decreases. Thus, we say speed is inversely proportional to time, or speed varies inversely as the time. Inverse meaning opposite. So here is the function defined by the form of the equation xy equals k, or y equals k over x. This is called an inverse variation. And as I said before, we say that y varies inversely as x, or y is inversely proportional to x. So if you look at these equations, you'll see that if k doesn't change, if x goes up, y has to go down. And here, if y goes up, x has to go down if k stays the same. So this is the relationship between inverse variation. The constant k is called the constant of variation, the constant of proportionality. It's the same thing we called it when we did section 8.1. Let's take a look at example 1. Before we do that, let's take a look at a graph. So this graph is what xy equals k looks like. Notice that as x gets larger, y gets smaller. And as x gets smaller, y gets larger. We'll look at this graph again back in up in section 9 when we do hyperbolas, because this is basically what this shape is. Example 1. If y varies inversely as q, and y equals 2 and q equals 6, find q when y equals 15. Alright, so the first thing you need to establish is what kind of relationship do we have? Well, it tells you it's an inverse relationship. So we need to come up with some sort of equation that describes the relationship. So we know that with inverse proportion and inverse variation, we know that y times q in this case equals k. If you look at the example from before, it was xy equals k. So just take the two variables, and if they are inversely proportional, you know that y times q equals k. So let's solve for k first. Let's plug in y is 2 when q is 6. So k has to equal 12. Now you just plug the 15 in for y using the same value of k, and we're going to solve for q. So 15 q equals k, which is 12. Divide both sides by 15, and you get q equals 4/5. So remember, with inverse proportion, the product of the two variables will equal a constant. In this case, y times q equals k. Joint variation. When a quantity varies directly as a product of two or more other quantities, the variation is called a joint variation. For example, if z varies jointly as x and y, then z equals kxy. So z is directly proportional to the product of x and y together. That is why it is joint variation. K doesn't change. So we will also say that z is jointly proportional to x and y. Thus, when the product xy increases, z increases. If the product xy goes down, z goes down as well. Now we can expand this. For example, if z varies jointly as x and the square of y, what would you write? You would write z equals k times xy squared, because now z is jointly proportional to the product of x and the square of y. So z equals ky squared. Now let's add another wrinkle. If z varies jointly as x and the square of y and inversely as u, so what you need to look at is you have the joint variation between z and xy squared, but you also have an inverse variation between z and u. So z equals kxy squared all over u. And this is the same for some non-zero constant k. So you might have to combine different things. Just work at them slowly, break it down into pieces, and it'll make it a little easier for you. Example 2. If r varies jointly as s and t and inversely as u, and R is 18 when S is 2, T is 3, and U is 4. Find S when R is 6, T is 2, and U is 4. Alright, so first we need to come up with an equation. So let's start it out by breaking it up into two parts. First, if we state that R varies jointly as S and T, how would you write it? R equals KST. There's your joint relationship. R goes up as the product ST goes up. Now, if R varies inversely as U, forget the S and T for a second. If R varies inversely as U, then, as we learned earlier, R equals K over U. So as R goes up, U goes down. As R goes down, U goes up. Alright? Now, all we need to do is combine the two equations together. And you basically just multiply this times this. And you get K times ST all over U. Now, the reason there's no K squared is because there's still a constant. So we still call it a K. But R equals K times ST over U. Alright, now that we have the formula, let's now plug stuff in. So all you do is plug and chug. First, plug in the variables you have for the first relationship and solve for K. So you get 18 equals K times 2 times 3 over 4. K is equal to 12. Now you substitute in 12 back in for K, and you solve for S. You have R, T, and U, so you solve for S, and if you plug all that in, you get S is 1. So part of the problem is figuring out what the relationship is in terms of an equation. Once you get that, it's just plugging stuff in, solving for K, substituting K back in, and finding the missing variable. Number 3, suppose R varies jointly as T and S and inversely as the square of V. When T is S, S is 18, and V is 5, then R is 3.78. Find R when T is 4, S is 12, and V is 4. Alright, again, like in number 2, you had to come up with an equation. So, let's again break it down into two parts. If R varies jointly as T and S, then R equals K times TS. If R varies inversely as V squared, since it's inverse, R equals K over V squared. Now again, you combine the two formulas together. So you get R equals K times TS over V squared. So remember the K's, when you multiply these two together, the constant still becomes just a bigger constant or a smaller constant. But different, it's still constant. Now you plug and chug. So, substituting in the values, you get 3.78 for R, T is 3, S is 18, V is 5. So 3.78 equals K times 3 times 18 over 5 squared. So you get K is 1.75. I'll let you solve that on your own. Meanwhile, you plug things back in, and again, now we're solving for R. So we plug in 1.75 for K, we plug in the new values for T, S, and V, and you solve for R. If you multiply all those things together, you get R is 5.25. So when you do these problems that combine joint and inverse variation, break the equation down into two parts and then combine them, and then just substitute, solve for K, and then solve for the missing variable. Number 4, a word problem. The time required to travel a given distance is inversely proportional to the speed of the travel. If a trip can be made in 3.6 hours at a speed of 70 kilometers an hour, how long will it take to make the same trip at 90 kilometers an hour? Alright, so before you even go anywhere, you should know that if you go faster, the time should be less. So make sure when you get your answer that your time is less than 3.6. If it isn't, then you did it incorrectly. So, first you need to write an equation. Let's let t equals time and s equals speed. If t varies inversely as s, we know that t equals k over s. There's the inverse part. K represents the distance traveled. So think about it. Speed times time equals distance. That's all k is in this case. So the distance isn't changing because it is given to you. But if you want to write it as an inverse proportion, here it is. T equals k over s. So now you use that equation and solve for k. We have 3.6 hours equals k over 70. Solve for k. K is 252 kilometers. So now we want to plug in 90 kilometers an hour for the speed. The k remains 252. We solve for t. T is 2.8 hours. And guess what? 2.8 is less than 3.6. So we're good there. So again, with inverse proportion, read the question, create the equation, plug, and solve. Example 5. For cones of equal volume, the height is inversely proportional to the square of the radius of the base. If the radius of a cone is 10 centimeters and its height is 15, find the radius of a second cone of equal volume with a height of 60. Alright, so again, you will want to create an equation. And if you're watching the video for the first time, go ahead and try to do that on your own. So let's call h height, and let's call r the radius of the base. So the height is inversely proportional to the square of the radius of the base. So if h varies inversely as r squared, then we have to write the following formula. H equals k over r squared. So again, read the question, identify your variables, and then draw the relationship. K represents the volume of the cone. We know that the cones are of equal volume. It doesn't change. So if you think of it this way, if you have a cone, the taller the cone is, the radius is going to be shorter. The shorter the cone, the longer the radius. Alright, so now let's solve for K. Plugging in the values, you get 15 equals K over 10 squared. K equals 1500. Now that you have K, go back and plug it back in. We want to find the radius. We know the height is 60. So 60 equals 1500 over r squared. R squared is 25, so r has to be 5 centimeters. So the radius of this other cone is 5 centimeters long. Final example. The surface area of a cylinder varies jointly as the radius and the sum of the radius and the height. A cylinder with height 8 centimeters and radius 4 has a surface area of 96 pi square centimeters. Find the surface area of a cylinder with radius 3 and height 10. Alright, again, we need to come up with an equation. We know that the surface area of a cylinder varies jointly as the radius and the sum of the radius and the height. So the jointly part means we have to multiply two things together. In this case, we have the radius multiplied by the sum of the radius and the height. So let's call A the area, H the height, and R the radius. If the product of the radius and height sum is the joint variation, this is what we have to write. A equals K times R plus H. Here is the joint variation. R times R plus H. Those are the product. That's the product that's going to vary jointly with the area. Alright, now let's plug stuff in. We know that the area is 96 pi. K is what we're solving for. Radius is 4. The height is 8. So solve for K, and you get K is 2 pi. Now all you have to do is plug it in. We want to know the area given a radius of 3 and height of 10. So 2 pi times 3 plus 10. And there's your area, 78 pi square centimeters. And this matches what you know about the surface area of a cylinder. Pi r squared plus 2 pi RH. Alright, in summary, from the last 2 days, we have direct variation. It is generally linear, and the ratio is y equals mx, or some nonlinear cases, y1 over x1 equals y2 over x2. Inverse variation means one goes up when the other goes down. The ratio is xy equals k, or y equals k over x. Finally, we have joint variation. It involves a product of two or more quantities, and their ratio is z equals kxy. Now keep in mind, you can combine these two to form something new, as you saw in several of the examples. That's it for section 8.2. Good luck on your homework.